Yeah, I agree. Okay, welcome everybody to this webinar for the Big Picture Consortium. My name is Geert Litjens, and work package leader of work package 4, which is on artificial intelligence and tools for the digital slide repository. And it's my honor today to introduce our speaker for this webinar, which is Stefan Doper, a PhD candidate at Radboud University Medical Center. He studied econometrics at Tilburg University and then mastered in data science at Radboud University, completing his master's degree in 2020. And since February of last year, he's been working in our group on the topic of weakly supervised learning, which in the context of digital pathology means learning with only slide level labels, so no pixel level annotations. And today he will talk to us about how you can do weakly supervised learning, different methods in computational pathology, and talk about a novel method we developed in our group over the past 2 years. So Stefan, the floor is yours.
Thank you. Just give me a moment to share my screen. Is the presentation clearly visible for everyone, and can you hear me?
Yes, but it's still in presenter mode and not in presentation mode. Or in preview mode. Now it's in presenter mode, and it was in preview mode. Now it's in preview mode again. Yeah.
I know how to fix this. 1 second.
And while, so sorry, while I'm speaking, just for those of you who joined later, please note that this session is recorded. So if you have a problem with that, then you have to leave or leave out your camera.
Yeah. So is it clearly visible now on the right format?
Yes.
Yeah.
Okay, great, thanks. Okay, so today's topic, as already announced, is going to be on the end-to-end learning for whole slide image classification. And that's something that we've been studying for the past year. And to give you a little bit of a contrast on what we've been doing for the last 10 years generally in AI when we're regarding classification tasks, it's been primarily on ImageNet, and the focus has been on throughputing as many of these images as we possibly can. There's of course a logical reason for this, because we have a lot of data in terms of natural images, and we can train very good state-of-the-art models on this. However, in terms of large input images, this is not really a great data set to use, because the images are roughly 500 pixels in either dimension. And recently I've been reading up on the transformers, and there was an interesting graph where they try to also scale their trained models onto higher image resolutions. And they've shown that they were able to inference on high definition image and video data up to 1600 here on the graph, 1600 pixels on either side, but well even into 8K. And so my question was then, is this really a relevant kind of architectural improvement when you're going to do something as whole slide image classification for medical imaging? So to put that into contrast, when you ask your pathologist to scan those tiny glasses of tissue samples for you, what you're doing is you're scanning at such a high resolution that a single slide is well into the billions of pixels. And a single slide on its own is actually already a significant portion of the entire ImageNet dataset. So what will happen if you try to do whole slide image classification directly using any kind of neural network is that when you try to even forward it, even at a batch size of 1, you're going to get, well, I think this error is known to pretty much anyone who's ever tried to train a deep learning model. You're going to run out of memory, because the amount of feature maps that you will have to save inside of your memory is just so huge that it's not going to work. So in comparison, if you look at ImageNet and the architectural improvements that they make and the tricks that they try to perform, it's simply not going to work for whole slide image classification, because it's in a complete league of its own. And something similar can be said, for example, in satellite imagery. So for today's topics, I'm going to introduce first 3 what we call workarounds, and I'll explain why we call them workarounds a little bit later. But the most, I think, popular method on how to handle whole slide image classification in, well, pretty much since the start has been to ask your pathologist to just annotate the regions of interest. Usually those are just like tumor regions. And once the pathologist is done annotating these regions, what the data scientist usually does is that we simply divide this whole slide image into patches. And with the information that you have gotten from the pathologist, you split them up into patches that contain tumor and patches that do not contain tumor, and use that to train your classifier. So the biggest probably bottleneck in that entire process, if you look at annotations, is you're not going to make your pathologist very happy with that, because in order to train a neural network, we know that you need hundreds, if not thousands, of examples for it to scale well. And if you have to make these kind of annotations day in, day out on giant images, well, it's incredibly time consuming and expensive. And not to mention, you're going to have a lot of problems to deal with as well, such as an increase in annotator disagreement, because the more detailed your annotations get, the more disagreement you will get between the annotators. And in the specific example of what I've just shown in terms of the model, when you're only training on patches, you are never taking into account the global context that you would like to have, because for some problems, it really relies on you being able to make an accurate analysis on the whole slide rather than just the local context from a single patch, which only the network sees, but never the global context. So this first workaround just really won't work when you want to scale it into practice. And it's also a bottleneck for research because you have to wait for these detailed annotations. So the next 2 methods, which are based on multiple instance learning and something called neural image compression, they try to solve this problem by only using the whole slide image label, which means that you will get some whole slide along with the label that there is a tumor, but you're not going to know where the tumor is at. That's something that the model will have to find out on its own. And I think that the most popular work on multiple instance learning early on from Campanella and others in 2019. This was at least one of the first successful ones. And what they tried to do is they patched all of the tissue samples that they would have in the whole slide image. And from these thousands of patches, they would run them all through a convolutional neural network, which I believe to be a residual net with 34 layers. And they ran them all through that network, and the network would output the probability that a specific patch would have a tumor or not. What they would then do is they would rank these probabilities, and they would take the patch with the highest probability of having a tumor, and they compare that with the whole slide label target. So what this means is that they compute the loss over just a single patch, and this has some negative implications, because what you're essentially doing in this method is you are forwarding thousands of patches into a model, which introduces a lot of extra computation time and overhead, only to filter all of these patches out which you consider irrelevant, and only to make a prediction on a single patch. And if you would draw the backward path for this, you will see that you will only ever backpropagate a single patch out of everything you've analyzed, which means it's incredibly inefficient. So the second way, and the way that neural image compression tries to solve this, again, first is by patching the whole slide image into smaller parts that can be put into a network. And what neural image compression tries to do differently is on the observation that you can use an encoder, which can be any kind of neural network or classifier that you would like, and you can use that to compress your patches into much smaller feature representations. So what you're doing here is you're using that encoder, and you have a patch of, let's say, 200 by 200, and you can compress that down to a single representative feature embedding, which will only be a size of 1 by 1 by any amount of channels, which is significantly smaller than what you started out with. So they repeat that for every single patch that you have in a whole slide image. And what you're left with is then, of course, these set of embeddings. And an optional step that they try to do is called stitching. And with this stitching, what they essentially try to do is to preserve these spatial embeddings that you might lose when you are compressing everything down. So what this basically means is that the feature map on the far right here is essentially, in terms of spatial dependence, the same as whole slide image classification. And this is useful because you can use this feature map to train a second classifier. Because this feature map is so much smaller than the original whole slide image, you can use normal backpropagation, which is actually quite smart. And because you preserve the spatial dependence, you can even train normal convolutional network if you really wanted to. So one thing to note about this is that this is not a whole end-to-end method. So first you have to train this decoder, which uses the feature map and the whole slide label separately from the encoder. So that brings us to the question, how would you train this encoder? And the way that we train it, the authors proposed several ways on to do this, consisting out of unsupervised, self-supervised, and even a supervised method. So what they basically try to do is a variety of methods ranging from GANs, variational autoencoders, contrastive, and there's many more ways that you can probably think up of now. And one supervised way that sadly requires the amount of annotations that we are trying to avoid. So it's probably not the best way to do it on the supervised way. And those are just a few ways that you can train the encoder as well. But the main thing you would have to remember here is that the encoder and the decoder are trained separately. And the encoder is still trained on just a local view on a patch-based level, while the decoder, the second classifier, is trained on a smaller representation of the whole slide image, which means it does get a global context. And one particularly successful way that CLAM has been applied, neural image compression has been applied, is through CLAM. The full name implies that it's multiple instance learning. However, I would see it as an example of neural image compression, but I think you would have to ask who you're talking to what they think it is. But essentially, this model is neural image compression at first. So what they're doing is they patch the entire whole slide image again and send it through an encoder, in their case, a residual net with 50 layers along with ImageNet embeddings. They do never train the encoder, which was surprising. And the smart part about this network is not only the neural image compression part, but also the fact that they use a smart decoder, a second classifier, which is based on attention methods. And the advantage of an attention module here is that you have two advantages, namely that you are able to give your model the freedom to select which regions in the whole slide images and which patches are relevant and which are irrelevant. And what it also implies is that you can plot these relevant and irrelevant regions, which means that you can get nice attention maps and a degree of interpretability, which I think is also important for the medical domain, that we also know at least basically what our AI is doing and not just treat it as a black box. And what you can see here is that they displayed a normal H&E stained image, which is standard work for the pathologist, along with their model output, which is the attention map, and an extra check based on a different staining, AE1, AE3, which tells you where the tumor is actually located in brown. And what you can see here is that the attentions, which are colored in red, are exactly or more or less on the same spots as what the staining would give, which means that the model has not only learned which slides contain tumor and which not, but have also been able to accurately locate which regions are relevant for tumors. And that means that we have another degree of interpretability, which is always nice. So as a sort of an intermediate benchmark, we can see how the performance goes from CLAM against multiple instance learning. And what the authors of CLAM basically have done here is they have tested their method on 6 different data sets with their own method against MIL. And what they did for each data set is that they held out a part of the data set. So they started with training with only 10% of their data set and worked their way up to using 100% of the data set, and showed that their method that the CLAM method is much more efficient with using the data compared to when you're using multiple instance learning. So now we're going to the part where we're going to towards streaming. But before that, I want to quickly explain what the problem is with these workarounds. Because even though we're getting more and more into the area where we've checked off all of the things that we would like, such as global context, we want to train the encoder and the decoder, and we want to be able to train a model without detailed annotations. However, even in the last few models when we're using, for example, CLAM or neural image compression, we're still not able to completely get the global context. For example, when we're trying to train the encoder, which is still done in a patch-based and most often unsupervised way. And all of these workarounds, they are mostly not even end-to-end, and they require some patch-based methods in which we try to get multiple models to work with together in order to come to a prediction. But what we are actually trying to solve in our eyes is we don't want these workarounds. We're actually trying to solve the memory bottleneck. So what we want to be able to do is to use this model that we're not able to use right now, but to just forward a whole slide image into a neural network and somehow deal with the fact that we need to be able to parse that much data through a neural network entirely and get a prediction in an end-to-end fashion. So before that, and before I really introduce the concept of streaming, I would like to quickly and briefly explain what happens when you're trying to parse an image which is too large for your GPU into a network. So what we're starting with here is just an image with a batch size of 4 images, and we're running it to any run-of-the-mill state-of-the-art convolutional neural network. And what happens at the first is that you will find that the number of channels increase quite a lot without the spatial dimensions decreasing in kind. In fact, that only happens when you go further into the network, when you apply pooling layers such as max pooling or average pooling, and only at the very end will you see that your features actually get very small. So the first few convolutions in your network actually take up the most memory. And this is also what happens then when you're trying to perform backpropagation, because it goes well at first. However, later on in your network, you're going to find out that the additional gradients that you're computing are just too large and you're going to run out of memory. So just for normal tricks, there have been several tricks have been invented, such as gradient checkpointing and gradient accumulation, to deal with this when you are running out of memory for normal images. But these are important later on because we're also going to use them for the method that we developed. So I'd quickly like to go over them. And the first one is called gradient checkpointing. And what we're doing with gradient checkpointing is we're going to define a checkpoint at some layer, and any layer before, any activation before that checkpoint is going to be computed and then thrown away as soon as we don't need it anymore right away. So this already introduces some memory that you can save immediately. And from a certain point onward, we're just going to continue with normal forward and normal backward passes. Now, of course, we need these activations. We need these forward activations to compute the gradients. So at the checkpoint, when we're doing a backward pass, we're going to recompute these features and then compute their gradients. So this saves a little bit of memory when you are almost able to fit something into a GPU, but not quite yet. And the second way is gradient accumulation, and this works on the observation that usually we try to forward an entire batch into the model at once. And the thing you can ask yourself is, why do we want to do that? So if you leave batch norm, for example, aside, the reason why we do mini batch gradient descent, of course, is because we cannot fit all data into the model. But also, if we only have a batch size of 1, the gradients often get very volatile and not really that smooth. And we want to have these smooth gradients for decent updates so we can stabilize training. So with gradient accumulation, what we're trying to do is we try to emulate the behavior of having a higher batch size by first just forwarding an image into the network and also doing normal backpropagation. However, we're not going to throw everything away, and after this first step, we're not going to do a gradient descent step, but rather we're going to save the gradients that we need into an array, and we're going to sum them up with all of the other gradients that we compute for the other batches. So at the end, when you've summed them all up, you can divide them, in our example, by 4, which means that you have a smoothed out gradient. So this is basically how you can train with a higher batch size with gradient accumulation. And this saves, of course, a lot of memory when you want higher batch sizes. So now we're going to the part that we've been working on, especially Hans Pinkaers. He's the developer of this method, on the method that he calls streaming. And he tries to answer, how can we solve the memory bottleneck? How can we train with whole slide images without these workarounds? And in order to do that, we have to look at a specific property of what convolutions can do for us. So what we see here is a large input image divided into these 4 colored regions. And what we're going to do is apply a convolution over this. Now the output will look like what you can see on the right side. You're going to lose some borders because of the convolution if you don't do any padding. And you can see that some of these colors overlap. Now, what we can do with streaming, and what the entire idea is you do not have to put the entire image in your network all at once after all. What you can do as well is you can simply divide this image into 4 color blocks that we have here in our example, and then apply the same convolution over each of these 4 individual inputs. What this does, and if you stitch these outputs back together, is the convolution over these 4 individual inputs with some overlap is exactly the same as if you would perform a convolution over the entire input image at once. I think this is best explained when we put it into the context of how you would train it using a normal neural network. And we can also apply the previous tricks of checkpointing and gradient accumulation from before. What you're doing is you're only going to take a small part of, well, let's say a large input image. Let's say that the input image that you have now would result in a CUDA error, an out-of-memory error when you put it into the network. So we're only going to take a small part of this, which we call just a tile. And you're going to compute it via streaming up into a checkpoint where your activations are small enough to be kept into the GPU memory. So you're going to proceed for each and every single tile until you have reconstructed the entire input and forwarded into your network. Now from this point onward, your activations is small enough to be kept into the GPU, which means you can continue with a normal forward pass and a normal backward pass. And of course, at the point where your activations finally get too large again, you can simply apply the concept or the property of convolutions. You can apply streaming and simply divide the input into smaller parts again, which the memory can handle. So this is in a nutshell what streaming does and how you can train with whole slide images. And to show that this is really equivalent to training a normal convolutional network using normal training, what they did is just a toy example on the ImageNet dataset, which you can see on the left side. And they compared it with their streaming method on the right. And you can see that the training curves and the validation curves are exactly the same, which is what you would expect. So there you can see that streaming is equivalent to normal training. So there are a few limitations of this method, primarily because you have to do multiple forward and backward passes when you apply streaming, which means that there is going to be some overhead and it's going to take some extra time for you to compute an epoch in comparison to normal training methods. The biggest drawback, in my opinion, however, is that you are not able to use some layers that many people actually use during training or during streaming part of the network. And these are dense layers, global pooling layers, and layers such as batch normalization. And the reason for this is because you need the whole input at once to compute their activations. There is, however, one workaround for batch normalization in which you just pull a state-of-the-art network that has been trained on ImageNet, for example. You use their pre-trained ImageNet weights, and then you freeze the batch normalization and do not train the batch normalization during the streaming time, during the streaming part of the network. So another thing is you can not use these type of layers during streaming, but you can use them in the non-streaming part of the network. So that's how you can still train these layers afterwards. So the next question is, of course, how does this algorithm apply when we're really going to apply it to whole slide images? And can we still use things like transfer learning, because ImageNet has, of course, been trained on very small images, so does it scale as well to higher images? And how does it perform to methods such as multiple instance learning and CLAM that we've seen before? So in order to answer that, they have done a study based on prostate cancer detection. They compared their method, in which they train a residual net with 34 layers directly using streaming, against the mill method that we've discussed earlier. And the whole idea here is that they are inputting their images with 16K by 16K, which is quite enormous. And they tested it on a prostate cancer detection dataset, which roughly consisted out of 5,000 training images and an additional test set of 500 and 200 images. They also performed a holdout experiment similar to before, which means that they trained on only a small subset of the data to see how well the algorithm scales. So in terms of the performance, they computed the ROC and AUC curves and compared it to MIL. In general, what you can see from these curves on the left side is that they tried using the streaming algorithm with only 5%, 10%, and the entire data set, and you can see that it still scales well, and even at a relatively low amount of images, it still performs quite well. The same holds in a similar amount to the multiple instance learning, which is the second from the left. And then they compared the methods directly, and I think that the most important one is the ROC curve completely on the right, where they show that the streaming algorithm far outperforms what you can do with MIL. So they also did an experiment with transfer learning. I'm not going to explain all of these numbers, but what you can do as a take-home message is that you can use transfer learning, and if you would train this model using streaming from scratch, it would still have slightly worse performance than if you use pre-trained ImageNet weights, which is of course good because that means you can use transfer learning and still get some gains from that. Finally, as in terms of visualization, they also wanted to make sure that the streaming algorithm learns the right features. So here you can see that using saliency, they were able to extract the features that were most relevant in this case, and you can see that that corresponds in many cases to tumor areas. So as a final study that we've been working on for the last few months, and then I'm wrapping up, is we were really impressed by what they did with CLAM because of the fact that it had some really good results, plus we were able to get some degree of interpretability as well, plus the fact that the attention decoder is able to extract relevant and irrelevant regions on its own. And we thought, okay, maybe it's a good idea to try and use streaming so we can train the encoder as well in a completely end-to-end fashion. So that is what we, in a nutshell, did. We really tried to push the streaming algorithm to its limits. So we took the largest input images that were still feasible, which means that we ended up at training it 65,000 pixels on either side. That's 4 gigapixels. That's quite huge, believe me. And we trained this on the Chameleon 16 dataset and tested it also on the testing part of Chameleon 16, as well as on the Chameleon 17 training portion, as an extra test of how well this model would generalize. And we tested our model against the base CLAM model, and we computed this for the ROC AOC curves and the accuracy. We trained our model at 0.5 micron resolution. And for those of you who like magnification, I believe this is equal to 20 times magnification. Please correct me if I'm wrong about this. But what you can see here is that in terms of accuracy and AUC, it far outperforms the CLAM model. So as an extra test, I decided to train CLAM at full resolution, so at 40 times magnification. And even then, the streaming CLAM version performed much better, both on Chameleon 16 as well as on Chameleon 17. So to wrap up, what I think the conclusions are with regards to streaming and the bottlenecks is that with streaming, you can really solve or come a long way to solving the memory bottleneck. Even if there are some kind of restrictions, you can theoretically train with 99% memory reduction as long as your tile size is small enough. And using streaming, all of the other stuff, such as transfer learning, can still be done. You can use gradient checkpointing, gradient accumulation. So it really fits in nicely with training other state-of-the-art networks normally. And although obviously some more research is needed, it seems to be performing much better than the workarounds that still do not quite accurately assess the problem of training with global context in an end-to-end fashion. So if you want to try this out for yourself, there are 2 GitHub pages, the Streaming CNN and the Pathology Streaming Pipeline on GitHub. We will be handing out these presentations to you as well after this meeting, so you can look at it for yourself. And for now, I'd like to give special thanks to Hans Pinkars, who's been a tremendous help over the last few months with helping me with streaming as well with some of these slides. And of course, to my supervisors, Geert Litjens, Jeroen van der Laak, and many others who've helped me in the last few months in the beginning of my PhD. And that concludes my end of the presentation. I'd like to thank you, of course, for listening to me babble on in the last 30 minutes about streaming and end-to-end classification.
Thank you, Stefan. I think that was a very nice overview. Of course, I'm slightly biased, so I'll open the floor to other comments and questions. Let me see if I can get a bit of a view of who's raising their hand. There is one raised hand from Mosin. Okay, I'm not sure if you can unmute yourself. Yeah, I think you can. So go ahead.
Thank you very much. It's very nice and very innovative method, and happy to hear this great talk. I just have one thing, maybe I have missed it. Usually we know that there are 2 problems. One is the memory bottleneck that you have solved very much, I hope. And second is the data. Deep learning requires a lot of data. When you reduce the patches and then try to get in the whole image, you left with very few images. Like in one of the cases, you showed that there was only 270 training set images. So how that 270 images are making the network able to learn?
Do you mean like in comparison to patches? Because with patches, you of course technically have a lot of data.
Yeah, usually it's millions of images that they say kind of on ImageNet and other things, like you need a lot of data to train a generalized model for deep learning. So here it's just a few hundred. So what's your thought? Like what's the reason that only 270 images were enough to learn the histology, the whole histology in the problem set?
Yeah, so maybe I skipped on that one, but I think what really helped as well is that we used pre-trained weights from ImageNet. So in the case that you had made with Chameleon, we only have 270 images to train. It was more or less fine-tuning, considering that we did use a ResNet 34 with pre-trained ImageNet, and I think that already helps a lot.
Yeah, okay. Yeah, that makes sense. Thank you.
Thanks.
I see two raised hands. Our first raised hand is from Jeroen van der Laak. So go ahead, Jeroen.
I'm not sure if I was the first, but
my screen says the first.
Can you tell us a bit? Still, I think it was a really great talk. I think you really tackled a tough subject very well. So kudos for that. Can you tell us a bit about data augmentation? I can imagine that data augmentation for whole slide images, if you want to do rotations or whatever, that it's really computationally extremely heavy, even to the point where it's infeasible. Is there a way to do it still with streaming, this end-to-end training?
Thank you, and thank you for your question. I think that's a very good question because I've spent quite a lot of time around this. And the answer is yes. I don't exactly know under the hood how it works, but there is a solution that's based on building a pipeline. It's called PyVips, and I don't know exactly how they do it, but it scales really well with multiprocessing. It scales really well with terms of memory. And even at training on 65K, I'm able to do augmentations quite well, and streaming, so training the network itself, turns out to be the main bottleneck. Of course, this is on quite a big and computationally heavy machine. We've been training on a DGX, which has a lot of CPU cores and a lot of GPUs. But from my initial training regimens, from what I've seen, is that it would still be possible. And if you're looking at other methods, such as neural image compression, these type of augmentations, especially rotations, you would have to keep them on disks, on your disk intermediate, because in order to compute those feature maps and then train them, of course, you would need to run those kind of augmentations and save those feature maps on your disk for each augmentation that you use. So I think that this is quite a step forward, in fact. Does that answer your question?
Okay,
yes,
good.
It did.
Then we move on to the next question, which is from Mustafa Yahanifar. I hope I pronounced your name correctly.
Yeah, it's Mustafa Jahanifar, but it's all right, Gerd. Thank you very much for the great presentation. I really enjoyed your method. I think it has it's very promising. So I have a couple of questions, but first off, I'm going to go to the augmentation. I had that in mind to ask you, but so I understand your answer, but I know that for some sort of augmentation techniques, you wouldn't need to do that on whole slide image level. For example, if you want to do brightness augmentations or stain augmentation or color jittering, these kind of augmentations you can do on those like tiles where when you're streaming, if I'm not wrong. Just some sort of suggestion, or to see if you have ever tried that.
Thank you. Yes, we've actually been thinking about that lately on doing that. We haven't tried it yet. It's the next step. And yeah, for now, we've been just using augmentations on the whole slide. So we first do augmentation on the whole slide, then throw it into the network. But I think your idea, so augmenting on the tile level, is definitely a good one, and that's what we're working on the next step.
I mean, even if you think of designing your model to extract, robust feature representations, you can even think of flipping the image or even rotating the tiles. That shouldn't change the representation. I mean, if you want your encoder to extract robust representations, then I guess even flipping and maybe even rotation can be done on tile level. But my main question was, sorry, I interrupted you. Go on.
I think it is possible, but you would have to think about how you would do the rotation. So if you would split your image into 4 tiles and then perform a rotation and then simply rotate each of these tiles, let's say by 90 degrees, then their spatial dependence no longer lines up. So you have to think about those kinds of problems as well.
Yeah, I agree. I agree with you. Those kind of augmentation like rotation would be much more challenging. You're right. However, so my question was, so I'm not sure if I get this right, but so you said something about batch normalization. I assume you haven't had included any batch normalization in your network, right? Because of the challenging that comes with the batch normalization.
We do, in fact, include batch normalization with a but. We just use the ImageNet weights for the batch normalization, and we then freeze those layers during training. And as long as you keep them frozen, there is no problem in using batch normalization in the streaming part of the network. Okay. So the next thing you might wonder, of course, does that really impact your performance? And for as far as I've seen, not as much as you would think. Mm-hmm. And even if you would look at the intermediate activations, so if you look at, for example, TensorBoard, you can plot the activations, they still seem to be squashed to more or less a normal distribution. So it doesn't seem to be impacting it that much, but of course the constraint remains is that you would have to use primarily ImageNet trained models if you really want to make use of batch normalization, because it still helps in stabilizing training, of course.
Yeah, how about, yeah, I guess it's a good approach that you have taken at the moment. But how about other different kind of normalization? So, we have layer normalization, we have group normalization, right? So I was thinking maybe you can come up with something like stream normalization when you just, again, focus on the tile, but it might be challenging as well. So just
yes, sir.
Suggestion to have in mind.
The author, the Hans Pinkaers, has warned me about this, that for the same reason as batch normalization, the layer normalization, group normalization are all not possible, or at least not easily. And for that reason, we haven't tried it yet.
Okay.
But yeah, you would run into the same problems because there would still be some cutoff point. So it's not as easy as using group normalization.
Okay, very well. Thank you very much. Just as a final question and very quick, how many epochs do you need to train this network end to end?
Well, we use a 2-stage strategy. So there is a part in terms of the streaming client model that we've trained. The first part is the ResNet 34, which you can load using ImageNet weights and the attention decoder of CLAM, and we initialized that randomly. So what we did is a first stage that speeds up training tremendously, and we only trained the attention decoder, and we kept the entire encoder part frozen until convergence. I think that it takes about 30 epochs, but that goes quite quickly considering you're not backpropagating through the encoder. And then as a final step, we also unfreeze the encoder part, and I've seen it converge as fast as 10 epochs.
Wonderful.
So all in all, I think on the size of Chameleon, it would take around a day or two. Of course, this was trained on a heavy system, so you have to take that into account.
Still impressive. Thank you very much.
Thank you for your question.
I see I'm muted, sorry. I was announcing the next person who can ask a question, which is Peter Schufler.
Oh yeah, hello, thank you.
Yeah, thanks, Stefan. This was really a nice talk, a nice overview. Again, my previous speaker just said it. Really nice talk. I have a question. Maybe that's also partly answered by one before. So usually, I would think intuitively, if you save on space like RAM, then you have to invest in time, like runtime, right? And so just wanted to find out if runtime is an issue. So does it take longer if you divide the image in smaller patches, or isn't that an issue here?
No, that is one of the limitations. So I'm assuming that you're talking about memory on the GPU, right?
Yeah. Yes.
Yeah, that is one of the limitations of streaming. So that's exactly the point that what you're saying. Because you're saving on RAM, you have to do multiple forward and multiple backward passes, so that introduces the overhead. And the second part is that it introduces overlap. And those things together do cause training to take longer. And we've optimized it as far as we can at this point. So it started out, I believe, where Hans tried to train it and it took about 8 weeks, and now it takes a couple of days. So I think that we've already made it as efficient as possible. But yes, that stays one of the problems, but I think it still tackles that the main advantage is still outshines the fact that you are having this overhead. But you are absolutely right, yes.
Thanks.
Okay, thank you for your question. I see there's one more person with a raised hand, which is Dr. Igor Zingman.
Hi, Stefan. I also enjoyed your talk. It was a very nice overview. And what I wanted to ask is regarding the architecture of pre-trained models you have used. You said it was ResNet, and I didn't understand exactly how it is possible to do. So the number of downsamplings in ResNet, I don't know, probably 5 or maybe a little bit more. So 5 times reduction of the size, or twice 25 times reduction in the size. But number of channels increases from 3 channel RGB to, I also don't remember exactly, but probably 1024 channels. So even the last layer still takes a lot of memory in this network, even more memory than the original image. Or you have changed architectures which much more downsamplings. This point I didn't get exactly.
Thank you for your question. That's very sharp. Yeah, you're right. The specific numbers is that the primary downsample at a ResNet is at the very beginning. So you start with a strided convolution, which reduces the spatial dimensions by a factor of 2, and then immediately at max pooling. In total, 32 times downsampling. And you are absolutely right. If you are left with that final feature map, it would still only be 32 times smaller in terms of its spatial sizes, and it has 512 channels in the case of the And what we did, and it might not be the most efficient way to do this, but we just introduced a large local max pooling after that feature map. So we used an 8x8 max pooling kernel. However, I would like to defend that statement that at that point, you've already have extracted relevant features and they will not get max pooled away. So yeah, it's
okay. So the output map, you just reduce its size with another max pooling with a big, relatively big mask, and then they reduce the amount of information.
Yes, so it might not be, again, the most efficient way of tackling it, but for our purposes, it still worked really well. And yeah, then you would get another, I think, 8 or 16 times downsampling, and then of course it quickly adds up. And what we're left with is, in the case of the input of 65K, after the encoder, the ResNet, you are left with feature maps that are 2K by 2K in terms of their spatial size. And after the max pooling, they are only 256 on either side with 512 channels.
I guess there's a large space here to play with architectures. Maybe it's then not pre-trained one, but for example, if you just increase the number of them samplings layers, then probably will be more relevant to the huge whole slide images.
Yeah, that's definitely a point of improvement. And we've also tried to do it the other way around. So we tried smaller input images and maybe a little bit of less downsampling. And the word's still out about that one. I'm still investigating that one, but it doesn't seem to be working as well as just using the best or the highest resolution as you can possibly get.
Okay. And at the end, which memory of GPU did you need to run your methods, streaming methods?
So we used the A100 GPUs for the biggest experiments. The point of streaming is you can basically or theoretically train it on even the consumer grade GPUs as long as your tile size that you pick is low enough. But of course you have to take into account the that you don't want to wait an eternity until it's done training. But I think it would be doable with at least a high-end grade consumer GPUs on inputs of 32K. It should be manageable.
Okay. And by saying tile size, so where do you use your tiles then? So the whole approach was kind of avoid tiling, but you say now that you have some parameter that refers to tile size.
Yes, what I mean with
size,
that
so.
is my presentation is still visible, right?
Yes.
This is what I mean with the tile size.
Okay, so when you did this convolution, you approached it on the partial. Okay.
This is what we mean with a tile. So these smaller inputs that will be added up together later on the network. That's still a hyperparameter, but you can pick this as small as the input downsampling of the network. That of course takes a lot of time. So you want to make this as high as possible, and then it will have the least amount of overhead, but it's a parameter. So it's that makes it theoretically possible to train it on even on smaller GPUs.
Okay, thanks, Stefan.
Yes, thank you for your question.
Okay, thank you all for your questions. Currently, I don't see any other raised hands, so I'm just giving everybody a couple of seconds to change that if they want to. Okay, it seems there are no further questions, Stefan. Thank you again for your very nice presentation and for eloquently handling all the questions. And with that, I think we conclude today's webinar. So I'd like to thank the audience for attending and hope to see you at the next webinar.